Hello, I'm Len Long, and I represent the Executive Committee of the IEEE Boston, which is the Institute for Electrical and Electronic Engineers, which serves 8,500 members in 29 different chapters and affinity groups. We cover topics of interest from aerospace and electronic systems, entrepreneur networks, women in engineering, and young professionals. We sponsor many conferences and several introductory and advanced engineering courses. These meetings are open to everyone, not just our members. IEEE Boston is pleased to present this discussion on climate change. Here is your moderator, Emory Award-winning TV personality and historian, John Horrigan.
For many years, the subject of climate change has evoked passionate debate. Have humans influenced our planet's climate, or do natural processes dominate our climate's dynamics? Hello, I'm John Horrigan, and on this program, we'll bring you two opposing views on climate change. Joining me are Paul H. Carr, B.S. MIT, Ph.D. out of Brandeis, IEEE Life Fellow. From 1967 to 1995, Paul led the Component Technology branch of the Air Force Research Laboratory in Bedford, Massachusetts. His branch's research on surface acoustic waves resulted in signal processing filters used in radar, cellular phones, and television. He's published over 80 technical papers and has 10 patents. After his retirement from AFRL, he taught philosophy courses at UMass Lowell, which inspired his book, Beauty in Science and Spirit. Recently, he participated in the climate change debate at the American Physical Society meeting at UMass Amherst and at MIT Lincoln Laboratories. In January 2013, he published Weather Extremes from Anthropogenic Global Warming in the Journal of Natural Science. His webpage is mirrorofnature.org. Ted Kochanski, B.S. MIT, Ph.D. University of Texas at Austin. Ted Kochanski is a consultant, educator, and entrepreneur with a background in experimental physics and extensive expertise in developing and utilizing multiple sensor technologies to characterize, monitor, and control diverse physical systems. His professional career spans tokamaks, University of Texas at Austin, Chair Technical Review Panel on Alpha Particle Diagnostics for Fusion Experiments, Defense System Analysis at MIT Lincoln Laboratory, Sensors Signal Systems with a wide range of domestic and international clients in technology, applications, intellectual property, entrepreneurship. He was a co-founder of several high-tech companies, engineering education, university, UNH and WIT International, continuing education at IEEE Boston Section, informal education at the Museum of Science Exhibit Hall for 20 years. So, Dr. Paul Carr, if you'd begin our discussion tonight on climate change.
Sure. I'm going to be talking about how we humans influence our climate. Our carbon dioxide emissions are happening 300 times faster than natural effects. The exploding population of 7 billion people is influencing our climate by burning fossil fuels that emit greenhouse gases, namely carbon dioxide with the abbreviation CO2. First part of my talk, I'll talk about the human influence on global warming. The emissions of greenhouse gases, CO2, are increasing at a rate of 2.5 parts per million per year. We contrast this with the slower natural processes, namely at the end of the Ice Age, from 18,000 to 10,000 years ago, CO2 increased at a much slower rate, 1/300th slower. And the third part of my talk, the impact of continuing climate change. The melting of the Arctic is increasing our winter and also, to a certain degree, our summer climate extremes. Part one of the human influence on warming. Now this is evident in this plot here. On the vertical scale, we have the CO2 in parts per million from the year 1000 to the year 2000, almost the present time. And as you can see, for about from about the year 1000 to around 1750, virtually no change. And then you can see this level here, although there was a slight dip during the little ice age when when our temperatures were cooler. But then around 1750, we started burning coal. We started when the steam engine was invented, we started installing railroads, and you can see the carbon dioxide starting to increase. By the way, the solid line here are the measurements from Mount Mauna Loa on Hawaii. These are the most accurate spectroscopic measurements, and the squares and the other symbols here are we get from the Antarctic ice cores. These are the air bubbles that are trapped in the Antarctic ice cores. As you can see, at the present time, 2014, our CO2 levels are 400 parts per million above the 120, and are therefore 120 parts per million above the pre-industrial average. And we know that from carbon isotope ratios that the carbon dioxide increase since 1750 is from burning fossil fuels. Fossil fuels are the order of 300 million years old. Here's a similar plot, though, on an expanded or different time scale from 1880 to 2010. The solid lines again are the carbon dioxide levels, and the wiggly lines are the temperature, which of course fluctuates. For example, this dip here was due to a volcano that erupted. You may notice that during this period, during the Second World War, there was no change in the average temperature. And this is attributed to the emission of aerosols mostly from coal burning, Germany, Japan, the United States, which continued on pretty much until the Clean Air Act kicked in. We started cleaning up our coal emissions, and the temperature started taking off at a very rapid rate, much more rapidly than, and this does correlate with the increase in the carbon dioxide levels. Well, how do we account for that? Well, one option is solar variability, but this article aptly shows that solar variability does not explain late 20th century. Here's satellite data. This is the irradiance, the total energy coming from the sun from 1980 to 2000. Different colors are from different satellites. The composite of all the satellites is this black line here. And you can see the expected 11-year solar sunspot cycle. But if you look at the peak to peak or the trough to trough, you see there's no, basically the sun's irradiance, at least during this time period, was virtually constant. So we can't explain the warming by increases in solar irradiance. So how can we explain it? Well, during this period, the greenhouse gases, namely carbon dioxide, were increasing, as you saw from the earlier slides. Basically, all our energy comes from the sun. About roughly half the solar energy is absorbed by the surface of our Earth, and the rest is reflected into space. Now, this energy absorbed by the surface is converted into heat, and heat is characterized by the emission of long wavelength infrared radiation, shown in the red here. Now, this infrared radiation is absorbed by the greenhouse gases. Some of it is emitted, lost into space, but most of it gets reflected back to Earth, and you get these multiple processes of reflection. So this is the protective blanket that keeps the Earth warm. We've also noted that over time, we might expect, as the greenhouse gas and concentrations have increased since 1960, the temperature of the Earth has increased, but the temperature of the upper stratosphere, interestingly enough, has decreased because less infrared is radiated into space, more of it gets reflected back to Earth. Here's a plot of the energy versus, or the energy density versus the wave number. Now, the outgoing spectral radiance at the top of the Earth's atmosphere that I was just talking to you about showed, and this particular plot shows the absorption of specific frequencies or inverse wavelengths. And you note that the biggest absorber is obviously carbon dioxide, this big dip here at 16 microns. And the heat flux, the energy flux, has a maximum very close to the maximum, to the absorption maximum of carbon dioxide. And that's the reason, as I'll show you in a moment, carbon dioxide is the key greenhouse gas. Other gases do play a role. Ozone has a dip here, and methane has a band. Water molecules come in. They have a distributed bandwidth. Well, let's now go to. By the way, this red curve is the flux of the classic black body radiation at the ambient temperature of the atmosphere. Here's a plot here of the radiative forcing of the climate between the beginning of the industrial age in 1750 and 2005. And you immediately note, and I explain why, that should come as no surprise, that carbon dioxide, which is a long-lived greenhouse gas that has a lifetime of the order of 100 years, has involves the greatest amount of energy. As you can see, the radiative forcing in watts per square meter is almost, it's about 1.8 watts per meter. I mentioned methane has a smaller effect, and you can see as you can just read these, the stratospheric ozone plays an even smaller role. These are all heating. These are all these gases absorb and heat the Earth due to the greenhouse effect that I just showed you. However, there are cooling effects, the land use, and also now aerosols. Aerosols, as I mentioned earlier, come largely from coal burning. They're particles in the coal, and they're big enough to reflect sunlight back into space. And so the direct effect, as you can see, since the sunlight isn't reaching the Earth, it cools the Earth. And the second effect is the cloud albedo effect, reflection. This is the fact that aerosols also affect cloud formation. And these are the error bars that reflect our relative lack of knowledge or lack of knowledge. The solar irradiance shown here increased only by 0.2% since 1750. All these data, by the way, are normalized to 1750. This is the so solar, a very, very small effect from the sun. Well, what we do is we take the warming, subtract the cooling, and this is the net due to human activities, shown here by this bar. And you can see that there is, even though there's a very large error bar here, there is within the range of error, the warming wins out, and that's why the greenhouse gases warm our Earth. So even if the cloud albedo effect is assumed to have a maximum cooling value, that would give us this point here, there will still be a net warming due to human activities. Well, we can see our carbon dioxide footprint in this atmospheric infrared sounder aboard the NASA's Aquila satellite. The red is the highest carbon dioxide concentration, 400 parts per million. And it's just where you might expect the maximum to be. This is the industrialized United States, Europe, and northern China. The rest of the world is a few percent lower. It's down in the green here, which is about 394 parts per million. So the CO2 concentration in the industrialized northern hemisphere is greater than the southern, and as one might expect, the temperature increase since 1880 of the northern hemisphere is 1.1 degrees C, whereas that of the southern hemisphere is only 0.4. Now I'm going on to the second part of my talk, which is changes in the Earth's tilt and orbit triggered by, which triggered the Ice Age warning. Now this is this part of my talk dealing with natural effects. This was a natural effect. Humans weren't involved with this tilt. During the steepest warming, and this all started with the Ice Age. On this plot, it's 22,000 years ago till about 18,000 years ago. We were still in the Ice Age. And this tilt triggered the release of carbon dioxide from the ocean. These points are the increasing carbon dioxide levels. And you can see that they were the leading indicator of the global temperature which followed and this carbon dioxide rate of change is about 1/300th the present rise which I showed you. This is a very slow rise compared to our present increases in carbon dioxide. The CO2 greenhouse effect drove the 3.5 degree increase in the average global temperature. And the sea levels, very importantly, the sea levels, due to the melting of the polar ice caps, were increased by the order of about 100 meters, which is about 328 feet. And for this reason, we have flood stories, the most familiar one being Noah. At about 10,000 years ago, our world population was only about 4 million people, and today it's 7 billion. So many orders of magnitude increase, and these 7 billion people all want to burn more fossil fuels to increase their standard of living. Here's another plot of CO2 concentrations against a more extended time scale going back 800,000 years. This is the end of the Ice Age that I showed you before, this is a different scale. This is the warming that took place between 18,000 and 10,000 years on this particular scale. And recently, starting, as I said, about 200 years ago, carbon dioxide emissions on this scale shot up vertically on this scale. Presently, we're at 400 parts per million, and we just do a linear extrapolation, and depending whether it's a lower emissions or a higher emissions scenario, we're going to get to about the order of 1,000 parts per million by the year 2100, or the end of the century. At the present rate here of 2.5 million parts per million, we humans are increasing the CO2 at a rate which is 300 times faster than the recovery from the Ice Age 18,000 to 10,000 years ago. Well, how might this affect our climate? Well, to answer this question, we go back in time now. Here we're going back. Each scale is 10 million years, and so that plot before I showed you 800,000 years would be just around here. So we see a warming trend here, CO2 when CO2 reached the temperature. Again, when the temperature and the CO2 reached 400 parts per million, we lost our North Pole. And when CO2 reached 700 parts per million, the Antarctic ice sheet melted. This is about 40 million years ago. And as you can see, at that time, the Earth was ice-free. There was no ice at the poles. Sea levels were hundreds of meters higher, or the order of 300 feet higher than they are today. I want to talk about the third part of my talk, which is the Arctic melting in the last 32 years. And here's a satellite photo of what the North Pole looked like in 1979. And this is a photo here of what it looked like, a satellite photo of what it looked like in 2011. As you can see, there's less reflecting ice. This was all ice here. So that reflecting ice, which reflected the sun back into space, is now become an absorber. So now the sunlight is absorbed, and it's become a source of warming, and that's why the North Pole has warmed twice as fast as the rest of the Earth. The Arctic is melting faster than the United Nations Intergovernmental Panel on Climate Change predicted back in 2007. Here you see their predictions and the observations. It's melting a lot faster than they predicted. So the UN Intergovernmental Panel on Climate Change, they tend to be conservative in their predictions because when you get the order of 300 scientists from over 40 nations, you tend to get a conservative prediction. Well, now I want to explain how cold air oscillating to the south, why cold air now. You've heard about these vortices and about the vortices, particularly during the winter time, of how the cold air comes south and as far as Atlanta and New Orleans, for example. We have a granddaughter there who reported an ice storm in New Orleans, and well, why does this happen? Well, it turned out in the past, when the Arctic was much colder, there was a large temperature gradient and an accompanying pressure gradient. Temperature and pressure are proportional to each other. There was a large pressure gradient which held the northern air, kept it up north where it belongs. But now that the Arctic has warmed much more rapidly than the equator, we have a very small temperature gradient, and so we get these oscillations, which of cold spells during the winter. And actually, some parts. I have a daughter in England who reported last year that they had a very unusually warm winter. She was in the warm side, and our granddaughter in New Orleans was on the cold side, at least for a few days. Here's a plot again of the change in temperature, the black, similar to what you saw before, and also the green is the sea level rise. And you see they're tracking each other with one notable exception, that since the year about 2000, the temperature increase has slowed down substantially, as shown by this vertical line. But the sea level rise, as you see, is continued and is even greater, has even speeded up. In other words, the slope of this line, the rate of sea level rise is faster than it was back in the 1960s. One explanation of this is so-called, by the way, of course, this melting is from Greenland, Antarctica, and the mountain glaciers. The climate scientist Michael Mann has published this article, "Earth Will Cross Danger Threshold by 2036. He's called this a faux pas because carbon dioxide levels are still increasing and warming is still taking place. So in conclusion, the UN Intergovernmental Panel on Climate Change just recently last year said it is extremely likely, that is 95% not likely, that human influence has been the dominant cause of the observed warming since the mid-20th century. I showed you this photograph of our human carbon dioxide footprint. Professor Richard Mueller's independent non-research outfit, nonprofit research group, webpage berkeley-earth.org, shows how all warming since the 1900s is due to human generation of greenhouse gases. Sea levels are rising and projected to increase 2 to 6 feet by the year 2100. And here's a quote from Paulson, a recent quote from Paulson, who was Secretary of Treasury under George W. Bush. "We're staring down a climate bubble that poses enormous risk to both our environment," which I've talked to you, and the environment, which he, being a banker and an economist, is very much concerned about.
Thank you very much, Dr. Paul Carr. And now, a counterpoint from Dr. Ted Kochanski.
Well, we just heard a very well-organized presentation from Paul Carr, and I'd just like to say that, if this was a courtroom, we'd have to have a rebuttal, but we're not going to get a rebuttal. What I'm going to offer is basically questions to ponder. In my career as a scientist and as an engineer, as an entrepreneur, an analyst of problems for people, the first thing we always want to do is ask questions. Paul's presented a scenario, and there's a lot of questions. A lot of the things that he presented as fact, a lot of people find incredible or less than credible. So we're going to try to address some of these questions, why some of these things are not quite so cut and dried. You shouldn't take the CO2 necessarily as being a cut and dried number. CO2 numbers exist from a lot of sources, and they don't all agree with the collections from the Antarctic and the Greenland ice cores. There are physical processes that occur, and those can affect the estimates of CO2 levels. So, some questions to ponder. How do we know that the global temperature is what it is? What's the climate? How has climate behaved in the past? What does the sun have to do with climate? It's not as obvious as it seems. How do we know that we did or did not do anything to affect the climate? And why should we or not care? So how do we know the temperature? Well, there's a lot of ways. One way we can say, feels like. Yeah, and if you're interested in knowing whether it's a hot day or a cold day, that's probably good enough. Instrumentation. Thermometry gives us ways of measuring temperatures for the last 400 years, essentially, and some of those temperature records actually go back to nearly that long a period of time. Most of them don't. We use thermometry for surface measurements. We use thermometry for airborne measurements from balloons. We also have an indirect sort of form of thermometry called satellite radiometry, which uses emissions of a particular line of oxygen that's monitored in the microwave part of the spectrum. You can tell me a story, anecdotal information. We have maps showing where people grew grains. We have data about the height of the levels on hills in Scotland where the lairds were able to get increased revenue as crop land as opposed to grazing land. We have archaeology. We have proxies, something that behaves reliably as a temperature indicator. We have holes drilled in the ice. Ice is a fairly poor conductor. We can actually measure the temperature of what ice was at the time it was laid down. We have isotope ratios, and we have tree rings and other things. So thermometry, well, there's a thermometer right here. This is a local garage in Lexington. Has a very nice thermometer, goes back probably in the early part of the 20th century when everybody needed to worry about antifreeze. And you can notice the very clear red line there where you want to be concerned. But we don't know, for instance, with that thermometer that the bulb hasn't shifted, so that if we look at the thermometer today, we're not sure that it's necessarily going to give us the same data for the same applied conditions as it would back, say, 50 years ago. We have lots of thermometry. This has happened one day in the wintertime, and we happen to have a collection of local measurements for New England. You'll notice that Boston is at 20 degrees, Rutland, Vermont was at 10, Hartford was at 9, Nantucket was at 24. It's very difficult to characterize. You say, well, it's around 20 or so, maybe 18 or so. But then there's Keene, New Hampshire, -4. Here's some other data in the same period of time in the wintertime, and you'll notice that there's a huge discrepancy in the temperature or gradient in the temperature between Logan and Medford, or Newton for that matter. This is the kind of thermometry that was used in the past. You'll notice on the left the traditional shed for the instrumentation. It was all manually collected. Modern instrumentation on the right. An example of some thermometry potential sources of error, and that is the cabinet painted originally with a particular type of paint, supposed to be whitewashed, and some have been left and have decayed to the point where it's mostly bare wood now. These give different amounts of emissions, particularly at night. Where are the stations located? This happens to be a particularly bad station in Pascagoula, Mississippi. It happens to be located modern instrumentation, but it's in very much of the center of an industrial area. You can see the data from it. And the recent temperatures are substantially higher. than they were back before 2000. Part of that is because of the change in the instrumentation, and part of it is because of the change in the surroundings. The instrumentation didn't move, the sewage treatment plant moved in. Where are the stations? Well, there's also a change in the number of stations. In the 1990s, the number of stations declined, and there was a dramatic decline in the number of stations in the northern hemisphere, and particularly in northern latitudes. Why? The Soviet Union ended. Here's a source of data that has been collected, number of stations around the country and around the world, a little less dense around the rest of the world, from balloons. And we have, in fact, in addition to the elevated data, we also have the calibration data that's collected when the balloon is held at the launch point. This is used to calibrate the radiosonde instrumentation against a standard thermometer, and it just happens that it also provides a temperature record that can be used to compare to other temperature records. We have satellite radiometry, as I pointed out. This is what the satellite data has given us. Two different independent analyses are shown, and you'll notice that the temperature changes very little until about 1998. Then there's sort of a step change, and then the temperature stays again relatively constant during most of the 2000 period. Meanwhile, CO2 went from 336 in 79 to 385 in 2008, and it's gone up some since. There's an anecdotal data. This is a shift of the oat crop failure with altitude in southern Scotland from 1650 to 1981, and you can see that there is qualitative information can be extracted from it, maybe quantitative information. You'll see the end of the Little Ice Age, basically, and then relatively unchanged since that time. And what is climate? That's a question we have to answer. Yeah, climate gives us a good guess at local or regional weather patterns. You know, I can say that in the summertime in Boston, it's hot. Of course, if I say the summertime in Boston it's hot to my sister-in-law in Houston, she laughs. Because she says, how many times have you had the temperature above 95? And I said, this summer? None. How many above 90? 4. And she says, 4? We had 4 last week, or 5 last week. So it's a somewhat of an arbitrary distinction as to say what constitutes the definition of climate. But we typically use the average on a sliding basis of 30 years for a given area. An example is basically climate in Wisconsin, which happens to be a site of a weather underground at the University of Wisconsin. The climate of Wisconsin in the winter is cold with occasional snow, warm in the summer with occasional showers. On the other hand, the climate of the tropical oceans is warm and humid almost all year round. And let's particular data from last winter. Here's some data from a couple of places that received a fair amount of snow and also had extreme temperatures. And this was from Kansas City and St. Louis. It's from a station in Missouri that was putting this information out on the website. But they got extreme conditions. This is Marquette, Wisconsin, and temperature data over the course of the last 40 or so years. Variation you'll see by the time of the year and the year. Here's some data just from this winter, different places, what the average winter high was, and the average and then the winter high, and the low temperature points. So this is the same kind of data collected over the course of the last 100+ years. Number of different stations reporting are color-coded that in terms of their rate of change or the largest change and estimated errors in the quality of the data. You'll notice that the quality of the data in the city areas tends to be very poor. That happens also to be the place where we have the most of the data collection, because that's where the people live. How has the climate behaved in the past? Again, is a station in Oakland, California. It's been in the same location for 100 years. No real dramatic evidence in change in temperature there. How's the climate behaved in the past? Same kind of data plotted now over the course of the surface of the United States. The color coding, the blue, very little change, and the red, rather significant increases. Again, red often concentrated in city areas. How the climate behaved in the past. Again, this is the central central England temperature. Goes back one of the longest temperature series that exists. You see what you see more than anything else is fluctuations. Very little of a trend. And data obtained from other sources in comparison here, sea level, tide gauges, medieval warm period, little ice age, temperature. This is from a paper published in 2009 by Grinstead. And you'll notice that compared to what was shown previously in some of the other earlier collection of data, some of the sources of the data are questionable. And this is going back further. How's the climate behaved? Temperature change, we've taken an average value from 61 to 90 and used that as the reference point and then compared temperatures. You'll notice that the temperature has been substantially above the current temperature range for the vast majority of the time. Indeed, the climate can be considered to be cooling to the next end of this interglacial period. This is from non-tree ring proxies, 2,000 years of global temperature obtained from various non-tree ring proxies. You can see the medieval warm period very clearly indicated when the Vikings colonized Greenland. You'll see the collapse of the colonies in Greenland during the Little Ice Age, and then a recent warm up again, not quite to the temperatures in the medieval warm period. Evidence from the medieval warm period from archaeology. This is a site in Greenland. It was a thriving community, and then it was basically frozen out, and it's only recently become accessible again. There's the timeline of the Viking colony in Greenland. You'll notice that it ended basically when the Little Ice Age began and in earnest in the 14th century. Here's an example of a site, a Little Ice Age site that's been excavated. The Little Ice Age was very prevalent in Western Europe. This is the Thames Frost Fair, which existed basically into the 19th century. The Thames froze solid. People colonized the ice and conducted activities, some of which were illegal because there was no criminal prosecution of people who did things in a place that had no jurisdiction. Some additional illustrations of the Frost Fair. This is February 4th in 1814. You can see the community there on the ice. These are various mementos from the Frost Fair. They were printed right on the ice. These are Frost Fairs, 24 winters in which the Thames was frozen over at London. It's not frozen over since 1814. This is 10,000 years worth of data collected from the ice core at Greenland. And you can clearly see the Minoan warming, the Roman warming, and the medieval warming, and they're all basically declining in peaks compared to the earliest era, right after the ending of the ice. 5 million years of climate change from sediment cores. See oscillations all over the place, and you'll also notice that the vast majority of the time the temperatures are far above where they are now. So how do we know we did anything? Most of it is based on models. Most of the models are somewhat questionable. Here's a set of scenarios showing predicted rises in temperature based on models after we collected the real data. And you'll note that in reality, the observed line substantially below any predictions by the models. This is again for data from 1979 to 2014, and you'll note a trend line has been fit to it, but it's far different than the CO2 line, which shows that if there is a correlation, it's a very weak one. Best fit in the most recent period is a decline in temperature from 2005 to February 2014. Average over the last 17 years and 6 months as of February was essentially 0. Various predictions compared to the observations. Most of the models are highly excessive. And the real world data is basically relatively flat. About ice, we heard that some people are concerned about the amount of ice. Well, this is measurements made by the University of Illinois, and this is the fluctuation in the amount of total ice coverage, and you can notice that there's essentially very little change in the overall amount of ice, vast larger fluctuation. This is a comparison of CO2 measurements with the temperature data, and you'll notice that maybe there's some sort of a correlation up until around 2000, but subsequent to that time, substantial deviation. One of the interesting things to note is the annual cycle in the CO2. This is very interesting here. I added this today because it's a measurement of CO2 from other methods rather than ice cores. This is from the stomatal frequency of the cells in the plant leaves that allow the CO2 into the leaf. And data has been collected from sources in Netherlands and Denmark, and you'll notice CO2 data collection ranges, the CO2 concentration ranges from 290 or even a little below up to well over 360 from historical periods. Again, the temperature plot compared to the CO2, showed that before, and showed that before, showed that before. This is another way to look at that plot. You could say, well, it's flat, and then there was an increase that occurred right around the time of the El Nino. It was a very large El Nino, and then again flat. Here's some comparison now in terms of the temperature compared to the Mauna Loa CO2 data. This is a close-up of the Mauna Loa CO2 data. You'll notice that there's variation, of course, on a day-to-day basis, but the main variation that occurs is, in fact, an annual cycle. So here's comparison of data based on beryllium and carbon-14 of temperatures going back to the time of the Ice Age, and also, temperatures of solar activity. So what about the sun? This looks like a picture of the sun drawn by an artist, but it's actually drawn by the sun. The colors are artificial, but this is a close-up of a solar active region. This is where it came from. This is the most recent Solar Dynamics Observatory giving us unprecedented quality data of time and spatially resolved. This is a flare, very dramatic increase in the output of energy from the sun. This looks like, again, another artist's conception, but it's real. Colors, again, are artificial, but you'll notice close-up of magnetic field loops, similar magnetic field loops. Plasma ejection from the sun. So, possible questions. How do we measure the temperature of something as big and complex as the Earth? It's not easy. Why are clouds so critical to the greenhouse effect? They dominate over all the clear air activity. What do we know about the sun and similar stars? And where did the carbon come from and where has it been? A lot of the people are going around saying, well, we know exactly where the carbon came from. We don't. Perhaps only 1 or 2% of the carbon in the carbon cycle is actually coming from human activity. How well do we understand the complexity of the climate system? We don't. And what is climate sensitivity for doubling in CO2? And then your insight. A small experiment in terms of complexity and a wrap. The sun plus water plus CO2 equals life. Let's not make a mistake and destroy our existence. Thank you.
Thank you very much, Dr. Ted Kochanski. Dr. Paul Carr, any counterpoints or rebuttal to Dr. Ted's presentation?
Well, you raised a very good question as to how we measure temperature and the urban heat effects and how that can distort the measurements. That brings up, I think, a very interesting story that our viewers can follow by going to Professor Rick Mueller of Berkeley, UCalifornia, Berkeley. His website is berkeleyearth.org. And he was very much concerned about the same problems that you issued. How do we measure temperature accurately? And to investigate this, he formed a 10-man research group, and he made a point of not taking government funding. He went to the Koch brothers, got some funding from them, he got some funding from Bill Gates Foundation. And after a number of years of research, he investigated all these various concerns that you very aptly described, and came to the conclusion that the four government agents, the three government agencies, namely the two in the United States, NOAA, GIS, which is the Goddard Institute for Space Science, and then the equivalent group in the United Kingdom. Actually, if you go to his website, all three pretty much agree, and these are independent organizations, and then he has his own take on it. I mean, he's basically looked at the data independently. You have the Berkeley temperature versus temperature, and they all agree. So you've raised a lot of issues, but I think as far as measuring temperature, I think he's pretty well resolved it, and people can go see for themselves. It's a very easy to understand website, berkeleyearth.org.
Ted, some comments on?
Yeah, well, I think one of the issues, again, is that it's not that simple. A lot of these people who are making analyses have never actually made a measurement in their life. I don't know anything about Professor Mueller. But there are plenty of examples of people who have done extensive detailed studies, for instance, on the shelters and what happens when shelters are not properly maintained. Again, the purpose of these things were not to collect data in the 1880s to be used to decide on whether or not we're warming the planet in 2010. The purpose of the shelters and the data collection system was to tell farmers when it was time to plant and when it was time to harvest, because frost was the challenge. We were still in the 1880s when these systems went into effect, essentially taking advantage of telegraphs so we could collect some data and put it in a central place. And this began actually during the Civil War for military purposes. And again, no plan for archiving, so nobody worried about these things. And the data collection is just unreliable in many, many respects. If you don't keep the shelter properly maintained, you will end up, for instance, with the shelter being overcome with trees or overcome with grass. Changes the properties, especially at nighttime. If you look at nighttime data versus daytime data, dramatic differences. Typically, urban heat island effects are far more extensive than people think they are.
Actually, another point, I was noticing one of your illustrations, you cited some temperature data from an article published in Science in October, I think it was March of 2013. And I made the point of looking at that. It's a very comprehensive article, and you showed some of their very interesting data. One of the things that I found very useful in that article, he was able to explain a physical mechanism for the Little Ice Age, namely that the currents, the Gulf Stream, he was able to document the fact that the Gulf Stream flow flowed in such a way that the temperature dropped by I think it's roughly 2 degrees, I think, or whatever it was. So he was able to explain the Little Ice Age as a result of a a change in the flow. Because as we know, Northern Europe, England, and so forth has the same latitude as northern Canada, and yet England has a much warmer climate, as we all know. So it was a shift in the Gulf Stream. And then there was another paper that I just read beginning of it was published in Natural. It was published just about the beginning of this year, in which he noted that that little ice age was also characterized by large volcanic eruptions, a lot of volcanic activity, which, you know, the aerosols cooled the planet. So it's a combination from these two papers. At least we understand the ice age a little better in terms of high volcanic activity and changes in the. But I would also at this moment I would like to repeat the claim of modern climate science, again the IPCC, that it's only in the last 50 years that humans have influenced our climate by our burning of fossil fuels. And a lot of these phenomena that occurred that you very well cited during the ice, there weren't enough humans around emitting enough CO2 to affect our climate. So I think you've illustrated via the night that there are a lot of natural factors that took place before 1950, but since 1950, I think I gave a credible argument as to why 97 they say 97% of the climate scientists basically accept the view that I.
Well, then how did the climate warm from the little ice age to the 1950s if your CO2 model wasn't involved? What was the factor that changed that allowed the climate to go from 2 degrees lower on an average or so than it is now to where it is today?
Well, it could obviously a shift in the Gulf Stream, because we now know England is a lot warmer.
Right, but when did the Gulf Stream shift back?
Oh, you mean yeah? I don't know if he had that.
See, I think that has to be another factor that drives the shift in the Gulf Stream, and I think one of the possible factors is solar activity. And we know, for instance, there was a very definitively dramatic change in solar activity that characterized the period around the little ice age. There were 3 specific minima in solar activity that drove a lot of phenomena. And as I said in my early statement, that sunspots and the brightness of the sun, which varies by about a watt or so per square meter, roughly a third of the so-called greenhouse gas forcing, between a solar cycle. During the Maunder minimum, it could have been down by 2.5 to 3 more watts. We don't know that for sure, because it's very difficult to extract the prior to the solar era, satellite era, the solar irradiance. We're getting data now from ice cores and from wood samples that we can extract isotopes of carbon and beryllium. But there's some issues about understanding these. And there's many possible sources that have to be incorporated in these things, and the models are just not nearly complex enough to explain what's going on.
If I could just interject here, we're in the middle of the second decade of the 21st century. Obviously, second world countries have become first world countries. There's 2x, 3x more automobiles running on this planet than, say, 30 years ago. A quantum leap in airliners flying over every day. Factories, coal-fired factories, emitting carbon dioxide into the atmosphere. But on the same side, to Ted's point, we are at the end of solar cycle 24. It's been a relatively dormant period of sunspot activity, hence the sunlight given out is somewhat weaker than if the surface of the sun were marred with sunspots. And there's been an increased activity with volcanoes over the past 3 years. Now people are getting worried. We heard global warming, and now we're seeing cooler extremes. Is this just an aberrational pattern with the climate where we're going from sine waves into sawtooth waves? Ted, your
Well, I would say, first of all, that we're on the downtrend. I mean, we're going to have more ice. It's coming. It's just a question of when. Is it coming in 1,000 years? Is it coming in 5,000 years? It's well past the average interglacial duration in this most recent ice age period. So we're going to get more ice. The question is, are we affecting things to the point where we slow that transition to ice, I don't think we're going to make an effect on that, because the interglacial changes on and off happened very rapidly. I mean, they happened, in fact, we had something called the Younger Dryas that happened after the end of the Ice Age, the beginning of the interglacial period, when we almost went back into glaciation. And changes occurred on the order of decades, not centuries, not thousands of years, but decades. So there were books published in the 1970s when we thought we were cooling into the next ice age that said the coming ice age. And they had various theories about it. I think the sun contributes beyond just the simple variation in brightness. We know the solar spectrum changes. We know that the UV component of the spectrum is dramatically different in the solar maximum and solar minimum. X-ray fluxes are different. The number of solar flares are different. And the solar wind capability of affecting the atmosphere. And you say, well, these are very second order, third order effects. We don't know the amplification components of these things.
So we've only got a minute left. We all have to reduce our individual carbon footprint. As a society where we consume and dispose, at some point, that's no longer tenuous. That it's, as a species on Earth, we're going to run and hit a brick wall one day, and that day could be just around the corner. Just closing remarks on that.
Yeah, well, I think the immediate challenge is climate extremes. The higher temperatures that we now have in the later 20th century means that there's more water vapor in the atmosphere. The vapor pressure curve tells us the higher the temperature, you have more. What does that mean? It means that when it rains, you get more rain, so that you are more apt to get floods. And when there's a hurricane, there's more rain in the hurricane. Similarly, so basically the idea is that hot areas get hot air. Wet areas normally, like New England, get wetter, and dry areas like the Southwest are getting drier, and we're seeing more droughts. Look at California right now. It's the longest and worst drought in recorded history. A normally relatively dry area is getting drier, for example. So we're having more climate extremes, and that's going to affect our agriculture. And then, actually, in today's New York Times, there is a report, a National Climate Assessment Report. And this report basically notes that the city of Boston, cities say from Boston, New York, if sea levels rise by like 1.5 feet, which is likely within 60 years, Boston, the property values in New York through Boston, New York down to Baltimore, property values are going to be the trillions of dollars of property value loss. And that's why our former Secretary Treasurer says that we're sitting on a climate bubble. That there are going to be huge economic impact. If all our coastal cities get flooded or lose property values, we're not going to have enough money to when we had Katrina, we had $150 billion to bail them out. But if all the cities need to be bailed out at the same time, that's not going to be possible.
No. Ted, your thoughts?
Okay, well, I think we have had an interesting discussion, and I think the key is really the fact that we still have dramatic uncertainties. I would argue that if you look at the IPCC data as presented in their reports from 1990 until most recently, they keep on changing what their estimates of their error bars are. And various times their error bars for clouds have increased and decreased to the point where sometimes the error bars extend over the zero line, so that sometimes you can't even tell whether clouds are net positive or net negative effect. I think we need a great deal more data and data processing tools in order to answer these questions. And the IEEE Boston Section is planning on developing a conference that hopefully will become a world center for the presentation of information, not about whether it's warming or cooling or whether we're responsible or not, but how do we make these measurements? How do we make these assessments? Because I think the key is the technology is coming around to enable a vastly greater world for these things.
Well, thank you for joining us with this IEEE climate discussion. A special thank you to New TV and to Dr. Paul Carr and Dr. Ted Kochanski. Thank you very much.